car with a trailer. So for the car with the trailer, so it is 2, 3, 4. The important approximation is on the angle group. What is the formula for interpolation entropy? Formula is the following. Then you take delta prime, which is delta delta, and you take one form omega that annihilates delta prime, and such that omega gamma dot equals 1. Again, there is a single one, and you consider d omega, and so to put the omega in intrinsic way in a skew-symmetric matrix, you cannot because you have a metric only on delta, but not on delta prime. So you have to construct a canonical metric on delta prime, but you can do it because you have an abnormal vector field. In that case, then you take this abnormal vector field, and from this abnormal vector field, so I call it E. You take G, which is the orthogonal of E in the distribution. E, the abnormal vector field, is in the distribution. In the distribution, you have metric. Then you can take the orthogonal of G, and the third vector field K is just a bracket over G. This is totally intrinsic. It defines a metric over delta prime. With this metric, you put this, with the help of this metric, you put this d omega under the form of a skew-symmetric matrix, and it has a single eigenvalue, alpha, and this alpha depends on W. This alpha depends on the point where you are on the curve, and the formula for the interpolation entropy is II of epsilon is 4 pi over epsilon cubed, sum of dw over alpha w, this guy. And again, if necessary, you have this logarithmic lemma, this logarithmic formula if there is a singularity. Again, I don't know if it can be in that case. Maybe it can be. This is the formula. So now, again, you prove that everything reduces to nilpotent approximation, and the nilpotent approximation is that in normal coordinates is given, is like that. It is, so x dot 1 equals u1, x dot 2 equals u2, y dot equals x2 u1 minus x1 u2. I usually put 1/2, and then you have z dot 1, which is this alpha. Sorry, you have w dot equals this alpha of w times. You know, we are in the two control case. Due to the normal form in two control case, you know a priori, you are sure that you have this x2 u1 minus x1 u2. The theorem about the normal form for a two distribution tells you that. Whatever. This is very, very useful to study this problem for distribution of rank 2. Times something. What is this something? You can, it can be x2, for instance. and you have this alpha W here. You can compute, it is like, maybe it is x1, but no problem. Okay. Then you have this system, and you want to go in the direction of the last component, and you want to interpolate in the direction of the last component. So by quasi-homogeneity, you can consider that epsilon is equal to 1, then you go to 1 in the direction of W. And then, how it works? Well, it is quite simple. You do as usual. You do like that. H dot 1. So these abnormals cannot do the job. They escape. They escape from the... You just check that the abnormals don't play any role. They escape from the curve from the vertical. Then they will be normal. So you have something like that: F1 U1 plus F2 U2, and you have no abnormal. So so what you want to do? You want to go in the direction of W as far as possible, and you want to come back to 0 for all other coordinates, the x, but also the y, because you want to interpolate the curve by a curve of length less than 1. And there are two ways to do the thing, but it is clear that if you interpolate and you go to 1 here, then there are two ways to see the thing. You can either maximize W, but you can also just say that it must be the curve that does the job, must be a geodesic of the metric. Why? Because if it is not a geodesic, a minimizer for the metric, it means that the minimizer will have length less than 1, will have length less than 1. Sorry, the length must be 1, or epsilon, whatever. Will be less than epsilon, and if it is less than epsilon, you can use the remaining to reach a neighbor. And if you reach a neighbor, it means that you do not maximize W. Then, by the way, the question was posed to me for both the metric complexity and the interpolation entropy. It is not clear at all that the minimum is reached. You posed me this question, yes. But of course, you can prove that minimum is reached in both cases, provided that epsilon is sufficiently small. It is standard capacity argument. Well, you have to play a little bit because of this interpolation, but there is a proof in our paper. Okay. And then you are looking for a geodesic. We are looking for geodesics that connect us from the origin to a point on the w-axis. That's it. And this geodesic cannot be abnormal geodesic. Then it must be a Hamiltonian trajectory of this Hamiltonian 1/2 pf1 square plus pf2 square. And we are in the level h equal 1/2 to be parameterized by arc length. And in that case, I change coordinates. So we know also that U1 must be PF and U2 must be PG. And since you are parameterized by arc length, U1 square plus U2 square is equal to 1, then you can set that U1 equals PF equals cosine phi, U2 equals PG is sine phi, okay? And as usual, you compute phi dot, and phi dot is just P FG, if I remember well. Is that true, Andre? You don't know? So, but okay. No, it is PFG, no problem. You can check. And so, in fact, PFG is curvature of the curve in the plane PFG. It seems to me that it is like that, and you continue, you compute phi double dot, and phi double dot is P bracket of F with Fg, U1, which is PF, plus, F and G, okay, sorry, plus PG with Fg times PG, and you check here that one of these guys is 0, and the other guy must be a constant. Why it must be a constant? It must be a constant, the other guy, because if you differentiate PFFG dot, then you get brackets over the 4, and you are nilpotent with 3 steps, all brackets over the 4 are 0, then this guy is a constant. Then what you get is phi double dot is equal to a constant times sine phi, which is a pendulum. Then you have a pendulum, okay? And first you have a pendulum, and second you have that x dot is equal to cosine phi, and y dot cosine phi, and y dot is equal to sine phi. Then what you have is an elastica. Other remark. This implies that phi dot is equal to C y dot, then phi is equal, no, phi is the curvature. No, phi is not, sorry, phi double dot equals Cxy, so phi dot is equal to Cy plus D, and then the curvature is a linear function of the position, okay? Previously, the curvature was a constant function in the previous cases. So for first bracket, optimal curve correspond to curves on the plane, on the horizontal plane of normal coordinates, to closed curves that have constant curvature. Now you have closed curves in the plane of normal coordinates that have linear curvature. As you will see, this continued, in fact. And so, in fact, here, these curves are just the Euler elastica. And what we are looking for, a periodic elastica, because we want x1 to x2 to go from 0 to 0, but moreover, we want also y to go from 0 to 0. And what is y here? Y is just the area this encircled by this curve, as you can see. Y is just the area of this closed curve we are looking for. So we are looking for one Euler elastica, periodic, with zero area. There is, so at this point there is a small detail that we missed for long and that I made clear when I saw you, maybe in Italy last time, because these interpolation conditions do not say that the curve must be smooth periodic. They just say that it must be periodic, but maybe non-smooth. Then at this point there is a small difficulty, which is not so small, because you cannot directly consider generalized transversality conditions for two reasons. First,
you should not explain me, because it starts.
Okay, but there is at this point there is some important detail. There is some important difficulty that will repeat in other cases, but I cannot enter into details. But okay, nevertheless, you can prove that actually not only it is periodic, but as soon as it is periodic and it maximizes, it must be periodic smooth. You can prove this. Okay. And then there is only one of this curve. Given a length, there is only one. It is clear that there must be two loops for the area be zero. Okay? And these are so the curve that gives you the interpolation entropy, and the formula, intrinsic formula, I already gave. Maybe before. Okay. Sorry, let me continue. Now, let us go to the 2, 3, 4, 5 case. Sorry, let us go to the 2, 3, 5 case. We remain with second bracket. This 2, 3, 5 case can be either, as example, the car. No, it is not. You told me something wrong. Okay? It is Boursa, your car is to train. It is not 2, 3, 5. 2, 3, 5 is the ball rolling on a plane, as I showed you on my first movie. It is the ball rolling on a plane. It is 2, 3, 5. And then
also the car with the trailer, if you connect the car with the trailer.
If you connect car not at the right place. Okay.
The different
I agree. Then in this 2, 3, 5 case, then in this 2, 3, 5 case, the important so you have similar it is very interesting, this 2, 3, 5 case. I will just say almost nothing, because you do the job, you get a formula, of course. The interpolation entropy is a certain invariant here, is a certain invariant here, times also 1 over epsilon cube, okay?
In 2, 3, 4 you did not write interpolation.
Sorry?
In 2, 3, 4, what is interpolation?
I told you, it is, you take this omega that vanishes on delta prime, and omega on gamma dot is 1, up to multiplication that is 1 along gamma. You have a single one, you put a metric on delta prime by introducing these 3 canonical vectors that you get from the abnormal flow. Then in fact you have a metric on delta prime. Via this metric you put d omega as a skew symmetric matrix, and it is a norm of this Q-symmetric matrix. You have this formula. Here you have other invariant that I do not detail, and you have the same formula. And what is very nice is that at this moment you have a present. Nature gives you a present. The present is the following. It is that this curve, the curves of the 2, 3, 4 case are also optimal for the 2, 3, 5 case. But you know, this is here we are looking from the curve gamma in the direction of the horizontal plane. Okay? In the 2, 3, 4 case, you can start from any point along this curve. It will not change the fact that the area vanishes because the area is the same. Here you have, if you start from this special point on the elastica, then the other moment, so you want to maximize this, but you have to interpolate this other one, y2 dot equal the other linear, x2 u1 minus x1 u2 times x1. And along this curve, you get as a present that this guy is 0. But you cannot start to have this unit symmetry property. You cannot start from any point of the elastica. You have to start from the singularity. And then, in fact, again, so these elliptic elastica, periodic, they finish to solve the problem in cohort 3. There remains no, but it remains nothing because remains a one-step 3 control case, which is codimension 3. It is clear.
And 2, 3, 4, 5 is also.
But 2, 3, 4, 5 is not generic. It is Gauthier.
Yes.
It is not generic.
It's not generic.
But it will come later. And 2, 3, 4, 5 actually is the car with the trailer. No?
Just 2 trailers.
It depends how to pull.
Yeah, but if you put it at the right place.
This trailer. Just 2 trailers.
With 2 trailers, sorry. But it is Gauthier. Then it will come at the end of my talk. All Gauthier, I have solution. So now we finish with generic situations of corank Atmos 3. It is finished. So I want to. What are my plans for the 5 minutes? For the 5 minutes that remain, I would just say it is almost finished now. How much?
You have 7 minutes.
Okay. So I just explained what I do in my last talk. So I will very quickly explain what happens. I will for a moment forget about the 2 control case, but continue with one step situation, one bracket, but more controls. And in particular, so with this very interesting 410 case, which is a free nilpotent case, with this 410 case, it is very interesting because you can see many things, but computations are quite difficult. One step, and after, in fact, it turned out that this result generalizes to. There is a result which is less precise, but you can compute the interpolation entropy, give asymptotic optimal synthesis, but less precisely, in the general case, less precisely than in the Fortin case. This Fortin case is interesting because, as I explained, not only it is never convex in the direction of gamma, but gamma never meets the image of the bracket, but intermediate cases are very interesting, especially the Forman case, where generically the following happens. Generically, along the curve gamma, you have open segments on which you are convex in the direction of gamma naught, and open segments on which you are not. Then the two behaviors come. It is very interesting. Then go to this Fortin case and to general one-step case. So it turns out that in one step, more or less, convex or not convex, we know more or less how to compute the interpolation entropy. It is, but I will not be able to give the detail. Then just maybe just state the result. And so after that, I go back to two controls, two dimensional distributions equals 2, but one more bracket. One more bracket is 2, but generic. I always consider generic for the moment. So 2, 3, 5, 6, which is the ball with a trainer. I have showed you the movie. It is extremely interesting. And there is something, a little miracle again here. It is that when you write maximum principle on the nilpotent approximation in the 2, 3, 5, 6, in general it is not Liouville integrable, but the particular case of the ball of a trainer is the integrable case. This is very nice. And so it is integrable, but it is not easy to integrate. But again, what you will have curve such that the curvature is quadratic function of the position now. But in general, this is not integrable. What is integrable is if it is quadratic function of the distance to a point. And it is precisely the case of the ball with a trainer. By the way, any curve, any problem, curvature is a function of the distance to some point is integrable. Function of the distance. This case, and after I will finish with the Gursa case. So if I have time, I give details. If not, I just state the results. And Gursa is the car with arbitrary number of traders. So including the 2, 3, 4, 5 keys. Okay, it's enough for today, maybe.